Valerie, which is perfectly okay as long as they don't call me Ms. As you can see, I'm Group Director of Science and Technology. As Reed mentioned, Inductoheat, although I'd like to clarify what does it mean, Group Director. I don't think. I represent a much larger organization than Inductoheat, which is called Inductotherm Group. And in this organization, I'm responsible for helping our companies around the world with projects related to induction heating and induction heat treating. This is why I'm a group director. And today I represent Radine, which is part of our group, as you can see here. But also you're probably well aware about other names of our group companies, such as Inductoheat, Welco, Thermotool, Lapel, and many other companies around the world. We are world's largest induction heating organizations. And here you can see not just offices, this is actually plants around the world. So I report to CEO of Inductotherm Group. And again, my responsibility is to help to develop new technologies related to induction heat treating and induction heating. Recognizing our knowledge and experience in theory of induction heating technology and computer modeling, we were invited to submit to publish materials in those handbooks. So as you can see, it's probably not very typical for a manufacturing company to participate in publishing books and chapters and handbooks which were published by professional societies. At the beginning, I would like to remind you very briefly the very basic principles of induction heating. And again, basic electromagnetic phenomena is quite simple. If you apply voltage to the coil terminals, there will be AC current flowing inside of the coil, within the coil turns, which will generate electromagnetic field in coil surrounding, not only inside of induction coil, but in close proximity to induction coil. And as a result, there will be eddy current flowing within the workpiece we would like to heat. And because of Joule effect, the heating will start. As you can see here, it is non-contact heating. One of the very basic phenomena associated with induction heating is skin effect. We call electromagnetic skin effect. Skin effect represents the area where 86% of all induced power will be generated. You can see here, I indicated that area will be heating, let's say, shaft or solid bar. On the left side, you can see the chart. On the left, this is a surface. Imagine this is a surface. This is a core. And this is a classical definition of skin effect, which shows exponential decay, having maximum power at the surface, and then power density or current density decreases according to exponential law. Again, this is a classical definition. In Industrial Heating magazine, Reed was my editor, we clarified this definition. It is classical definition. However, there are exceptions. In the surface hardening, there is never exponential distribution of eddy current or heat sources. But because time limitation, I will not go into this discussion right now. You will stop and see me at our booth, and I will describe to you the specifics. Here you can see animation of skin effect. Solenoidal coil. Inside of solenoidal coil, there is a cylindrical solid body, and you can see clear indication of the surface layer with maximum power density and temperature. Mathematically speaking, current penetration depth represents skin effect. It is quantitative parameter that associated with skin effect. As you can see here in the metric system, current penetration depth, which is area where 86% of all power will be induced, is function of electrical resistivity, relative magnetic permeability, and frequency. Again, higher electrical resistivity results in greater current penetration depth. This is the reason why when we're heating aluminum, copper alloys compared to titanium or a super alloy, nickel-based super alloys, for example. The current penetration depth is much smaller when we're hitting copper or brass or bronze or aluminum compared to titanium or stainless steel, non-magnetic stainless steel, for example. Another factor is the relative magnetic permeability, which means magnetic materials will have much smaller current penetration depth or much smaller area where 86% of all power will be induced compared to non-magnetic materials. And last but not the least is frequency. High frequency results in lower current penetration depth and vice versa. As you can see here, there is no thermal parameters involved. There is no specific heat, there is no thermal conductivity that related to current penetration depth. On the left side, on the right side, you can see the area where the hardened layer show. This is hardened layer, and in induction hardening, which is one of the largest area of induction heat treating. Induction hardening, current penetration depth, is probably the most important factor to provide required case depth. Is the current penetration depth constant value? No. Because it's function of relative magnetic permeability and resistivity, and those physical properties are function of temperature, current penetration depth, when we, for example, heating metals, steels, especially carbon steels, increases with temperature. In the beginning, there is a slight increase because electrical resistivity increases. Then there will be a drastic increase in the current penetration depth because magnetic properties will be lost. And this, as you can see at Curie temperature, will be the area with the almost greatest current penetration depth. Then there will be slight increase continue because resistivity continue increasing with temperature. How big is the increase? With carbon steels, it can be up to 15 times. So this is how important to properly treat this parameter. At the beginning, for example, at the beginning of heating, if current penetration depth at given frequency is 1 millimeter, at end of the heating is 15 millimeters. So this is very important and to understand because this inappropriate consideration of current penetration depth as function of temperature results in lower electrical efficiency because current cancellation takes place if frequency chosen incorrectly, or in inability to achieve complex hardening pattern. Of course, in induction heating, this is only a small portion of almost endless variety of parts that can be induction hardened or induction heat treated. Because there is almost endless variety of parts which can be induction heat treated, there is almost endless variety of induction coils. All these coils used for different applications to provide required heating patterns. How can we qualify all processes related to induction heat treating and induction hardening especially? Based on the heating modes. There are 4 heating modes in induction hardening: static or single shaft heating, scanning mode, progressive heating, and pulsing mode. Static heating, we can induction harden using static heating quite complex shaped parts. You can see here, this is a cam, and this is induction single-turn coil, static heating. You can see a nice case depth. Even this type of part, which might look very difficult to induction harden, no, look at this pattern. Hardening of working faces such as wrench jaws, hammers, also very often undergo induction hardening processes. Scanning is the second but not as least important process. You can see in scanning process we have in this case 2-turn induction coil, quench ring and quenching process taking place. This is a induction hardening of flat surfaces, and this is an example of the shaft being after being induction hardened. Coils, induction coils or inductors can be quite complex or quite simple. Even in case of single-turn coil, as you can see here, it looks like very simple single-turn coil it is quite complex area. This is a heating phase. This is a water cooling pocket. This is a quench pocket and quench holes right here. This is a typical result of induction hardened pattern using scanning technique. But today, at this point, I would like to complete discussion about something you might already knew because of basics or very conventional applications of induction hardening. Now we are going to talk about something about subtleties, about subtle technologies, subtle applications of induction hardening. Let's imagine we need to induction harden output shaft. And as you can see, it has quite complex shape. Different areas of the output shaft might require different case depth. They might have a different thermal heat transfer properties because certain areas are whole areas with very small cold sink effect. Some areas are solid areas. As you can see here, there are splines. And typically, up to maybe last few years, the all induction heating manufacturers had only two parameters to control case depth. And again, depends upon applications. In some cases, case depth might be 1 millimeter. In other areas, it might be 3/8 of inch, 3 millimeters, maybe 5 millimeters. How can we control case depth in scanning applications? Using scan rate and power. Change the scan rate and change power, we can control case depth. If we need a deeper case depth, usually we would use lower power density and slower scan rate. We need a smaller penetration depth, smaller case depth, we'll use high power density and high scan rate. However, it would be nice, as we discussed earlier, that current penetration depth affects so drastically optimal pattern, induction hardening pattern. It would be nice to be able to change frequency on fly, not just to have capability to change power and scan rate, but also to be able to have a capability to change frequency. In this case, we don't have to lose production to slowing down scanning rate, or we can optimize heat treating microstructures because we can precisely generate power where it's needed. This is a solution. As far as I know, this is a patented technology. As far as I know, this technology is only available from our group. And we call it IFP inverters. So this is, IFP stands for independent frequency and power control. As you can see here, on the bottom, we can use like a CNC machine. You can program a CNC machine. When you're scanning your shaft, for example, you can program it as CNC machine, change not only power and scan rate, but also frequency. And frequency changes from 5 kilohertz to 50 kilohertz. At this point, maximum power is up to 300 kilowatt, which just covers most typical application of induction hardening. So that was a long-lasting dream of heat treaters. As I said, you can just program it as a CNC machine. You're scanning at such and such rate, at such and such power, and such frequency. At the beginning, maybe 5 kilohertz. You need deep case depth. Then you have a hollow area with very small mass of metal to be heated. You want to increase power density and increase frequency to 50 kilohertz. So that technology really helps to optimize induction hardening process parameters. And also it provides greatest process flexibility. Of course, with induction, we can easily incorporate protective atmospheres, nitrogen, hydrogen, argon, into induction heating process. You can see here, this is a chamber that allows to have protective atmosphere when we are heat treating certain component. Protective atmosphere can be designed to be inside of the coil or outside of the induction coil, it doesn't matter. One of the newest technology we developed, it's extremely successful technology, we help our company to relatively easy go through that downtime time when economy had so much struggles because we have patents, several patents for this technology. It's induction hardening, non-rotational hardening of crankshafts. But this technology is not only limited to crankshafts. It can be used in camshafts, it can be used in induction selective hardening of tubes and pipes, and several other components. This is how it has been done in the past. In the past, conventional there are two ways to do induction hardening of crankshafts. Again, I'll be referring to crankshaft, but keep in mind it's much broader applications can be used. Using clamshell coils. This is clamshell inductors, very old technology, used since 1950s. The problem with this technology is that there is a break of the current flow because we have to open and close clamshell coil. And that results in very poor life of induction coil. Usually, a couple thousand hits is the maximum that coil can take. And again, repeatability is questionable. The more typical process used in the past is using U-shaped inductors. You can see on the left, on the right side, on the bottom, right here, it's U-shaped inductor. And basically, this is all very bulky structure. And induction coil physically rides on a crankshaft. The reason why people have to use clamshell inductors or U-shaped coil because it's impossible to load crankshafts and have a very small, required small air gap between coil and the journal required to be hardened because the counterweights, they're so big, you cannot have such a small air gap. This was a solution for hardening of the crankshafts. One of the concerns which customers had who used this type of technology, look at the coil. There are carbide guides. Air gap is less than ½ millimeter. It is very difficult to monitor those less than ½ millimeter carbide guides. If wear takes place, and it's wear always takes place, but if wear wasn't monitored properly, then coil copper start to ride on hot surface and coil failed. But it was even more dangerous that the water leaks start to develop slow, and some crankshaft might have problems, and maybe customer won't get it, will not catch it fast enough. And of course, another big issue with this technology was high maintenance cost. Because imagine so many features and so many cranks, and everything moves, and coils actually physically rides on the feature. And power has to be changed at each coil, depends upon what position it has, because the counterweight has different side masses. Obvious disadvantage of carbide guides, the shortcomings of carbide guides is related to specific setup training required. After you replace coil, it takes some time to make sure that new coil provides required results. And it's almost the chance for human error. This is what we decided when we talked to customer we wanted to do. We want to improve reliability of those technologies. We want to increase coil life dramatically, not a couple thousand hits, not even a couple 100,000 hits, but 100,000 hits. Maintainability should be improved, and we want to decrease life cycle cost of this technology. This is what we've done. And this is patented technology that allows to provide better process, better cranks, and better machine. And we call it SharpC, Surface Static Hardening Process for Crankshafts. Basic idea is very simple. As you can see here, on the right bottom, the green area, and it's a bit, I don't have a laser. Coil consists of two circuits. One circuit is, we call it active circuit. It's connected to the power supply. Current flows in this circuit this way. And we will position crankshaft feature, journal, main, or pins in these areas. The top circuit is a closed loop circuit. There is no connection to power supply. When circuit is opened, we can easily locate crankshaft features in the areas required to be heated. After we located position crankshaft features, we closed top coil. And now, as you can see, crankshaft pin or main sees perfectly uniform solenoid-like coil with very good coupling, but we are not breaking any electrical contacts. This is why coil life will be low. And we have a special area when we use laminations, or we provide magnetic coupling. It's like a transformer design. Many times very simple ideas results of phenomenal, provide phenomenal results. This is how it's look. As you can see, the top is just a single shot loop. There is no power connected. Power connected only to the bottom. Each coil hits two features, two journals at the same time. In this case, we are hitting 4 journals at once. The closing top passive coil and heat will be connected and heating will be done. Because this technology has it's obviously a very simple, beautiful idea, but there are much components, much know-how were involved. This is only 2 patents, 61 claims in one patent, 30 claims in another patent. We have 4 patents in general related to different applications of this technology. One of the beauty of this technology is a very short heat time. Now we don't have to have a U-shaped coil that infinitely heats only half of the crankshaft feature. It has to wait when thermal conduction allows to have a uniform heating. I have about 5 minutes left, so I'll be a little bit faster. And I would like to use my time to present materials, and we'll answer questions later at our booth. Again, heating time has been reduced from 3 to 5 times. This is actually how it will heating will look. Heating, quenching, done. Feature has been hardened. As you saw in previous slides, the U-shaped coil has a lot of very complex geometries. With Sharp-C coil, we use CNC machine, coils are CNC machines. We have a solid copper bar, CNC machine very precisely. Doesn't matter if operator is sober or not quite sober because a good party last night. So CNC machine always does precise job. And this is how coil look like. If you can see comparison of the old design with very complex bended and braced joints, there is no brace or bend joints here. Everything is CNC machine from solid copper. Also, there is no carbide guides. Much larger air gap, improved coil design. So it's very robust process. And also reduce distortion of the coil during manufacturing because there is no bending. Regardless how experienced operator might be or machinist might be, the bending is very hard to repeat it during brace operation. Depends upon the crankshaft. We can harden, you can see here, several options. In 3 stages we can harden this crank. And by the way, because heating time is so short, usually less than 4 seconds, because we're heating solenoidal coil basically. Distortion is less than 0.025 microns, a millimeter, so 25 microns distortion. Almost there is no distortion. There is no strengthening required, which is cost savings. Here you can see also V6 cranks, and will be induction hardened in 2 positions. Pellet maintenance. You can see here it's very easy to replace pellets. Disconnect 2 hoses, loosening fuel clamps. Inoperative pellet is easily removed, and functioning pellet is then put in place. So a couple of minutes replacement is done for new crankshaft feature. This slide shows microstructures. One of the customer gave us presently use a structure using rotational technology. And this is the area most critical because the cracking always takes place. Not always, but it's more prone area for cracking. And cracking also related to grain boundary liquation if surplus of temperature occurs. So you can see here non-rotational technology, microstructure, and rotational technology. And of course, this is you can see the hardness pattern, very uniform. And we can talk a lot about technology itself, but it's easy to see how it operates. It's fully automated. We see a gantry, picks up the already heat-treated crank. Will be loaded new crank. Again, remember 4 features will be 4 journals will be hardened at each station. It closed, right? Station closed. Now it's heating for quenching. Now you can see quenching. The steam is coming, and then it's tempering. So it does all things at once: hardening, quenching, and tempering. So very high production rate machine. And crankshaft, what is one of the biggest beauty of this technology, because distortion is very small. Also, I have since I have 1 minute left, I would like to briefly describe you another technology. This is almost classical slides we published. I published it in Industrial Heating magazine 12 years ago. It shows the variety of hardening patterns that can be achieved with induction hardening. You can see the proper selection of frequency we can harden flanks or tips or fillets. And this slide shows the typical technology used. Conventional single frequency, pulsing dual frequency, and simultaneous dual frequency. And now we have technology that allows to have at coil 2 simultaneous dual frequencies at the same time to provide required hardness pattern. So here you can see how it's done. One power supply has 2 modules. High frequency module, which provides 150 to 400 kilohertz frequency, and medium frequency module. Again, in that case, it was 600 kilowatt, 10 kilohertz. Induction coil sees 2 frequencies at the same time. You can see here voltage, coil voltage, and coil current. This is your 10 kilohertz, and this is your 400 kilohertz frequency. And this is a machine that does it. The beauty of this machine that when we induction hardened the pattern, the part that in this case the customer was Linamar Corporation, they allow us to use it, they name, and you can see process recipe. During 0.8 seconds was only 10 kilohertz applied. After 0.8 seconds, both frequencies, 10 and 360 kilohertz were used. As a result, distortion was, actually you can see movie, loaded part, heating, quenched. And distortion was only 80 microns. So this technology allows to provide true counter hardening or to minimize distortion, because less metal is heated, less distortion will be. Well, because my time limitation, I have to stop my presentation. And I would like to invite you to stop at our booth 300, 302, and I'll be more than happy to answer your questions. Unfortunately, we don't have time. I chose to present more materials to you, so you'll be aware of these technologies. If you will have questions, please stop and talk to me. I'll be more than happy to answer questions.